Okay, so last week we have talked about AVL trees and splay trees. So the point is to speed up dynamic searching by maintaining a balanced tree so that the height of the tree is big O of log n, and therefore all the operations can be done quickly in log n time. AVL tree was the first so-called self-balancing tree. It defined the word balance by saying that the left and right heights must be close, that they must differ by at most 1. And then we can prove that this kind of height balanced tree is indeed good, meaning that its height is indeed log n. Splay tree is like a simplified version of AVL tree. What's so special about splay tree is that it simply doesn't care about what balancing is. Yet its overall performance is as good as an AVL tree. On the other hand, there are many other ways of defining what balance is. So today we're going to talk about two other search trees that are also balanced and actually more popularly used in real systems. So here we are, red-black trees and B+ trees. Let's start from the red-black trees. Well, say if you know the STL in C++, you should know that red-black tree is used in implementing several library functions such as map or set. Or in C#, it's used to implement the sorted dictionary and so on and so forth. So why would people prefer to use red-black trees, not AVL trees? Let's see. So the target of red-black tree is still to speed up dynamic searching and therefore to maintain a dynamically balanced binary search tree. So first of all, it's a binary search tree. And secondly, it must be balanced. So this is the tree node structure of a red-black tree. Besides the normal space for the key value and the left child pointer, right child pointer, it also has a parent pointer. And the most important part is this color field. There's 1 bit to tell the color of this node. And in your textbook, there's another name for the null pointer. It's called nil. And nil is considered an external node with the color black. So this is the definition. Say a red-black tree is a binary search tree, first of all. And it satisfies the following red-black properties. There are 5 properties. First of all, every node is either red or black. That's why it has this name. And the root must be black. And every leaf is black. Here, the leaf node is different than the normal leaf node we were talking about for an ordinary tree. In the red-black tree, we consider every null pointer, every nil, as a leaf node, and their color is black. And then these are the two most important properties. One is that if a node is red, then both its children must be black, meaning that along any path, we won't see 2 red nodes sitting one next to another. And the last one is the most important one. For each node, all simple paths from the node to descendant leaves contain the same number of black nodes. That is the key property that guarantees that a red-black tree is somehow balanced. Now to see that if you have really get this definition, let's have a quick test. So is this one a red-black tree? And the answer is simple. Certainly yes, because it's easy to see. How about this one? This is no longer that clear. And it's certainly not an AVL tree. It's not so balanced. But if we count the number of black nodes along each path, we have 1, 2, 3, all those paths, every path contains the same number of black nodes. So the answer is yes, this is a red-black tree, although it looks less balanced than an AVL tree. And here the real tree nodes are called internal nodes, and those null pointers, say the new nodes, are external nodes, and they are considered to be the leaf nodes in a red-black tree. So the most important concept in the red-black tree is the black height. We define the black height of any node X to be the number of black nodes on any simple path from X down to a leaf node, down to a new node, where X is not included. And the black height of the whole tree is the same as the black height of the root. And then we have this very important lemma. We say a red-black tree with n internal nodes has height as most 2 times log of n plus 1. That tells us what? Tells us that even though red-black tree is not as balanced as an AVL tree, still it is sufficiently good because the height is guaranteed to be big O of log n. And the proof of this lemma is interesting, so let's go through it. First of all, we like to prove that for any node X, the size of X means the number of internal nodes in the subtree rooted at X. Okay, so it's the size of that subtree. The size of X is bounded below by this number, is 2 to the power of the black height of X minus 1. Let's first try to prove this by induction. When we use induction, first of all, we have to prove that this is true for the smallest case. If the tree height is 0, means that the tree is empty and X is null, and therefore the size of X is 0, and the black height of X is also 0, so they are equal, and therefore this inequality is true for an empty tree with 0 height. So we are done with the smallest case, right? Okay, what do we do next? We should assume that this is true for all X with some height that is smaller than or equal to some integer k. And then we want to prove that this is also true for k plus 1. Then for any X with its height being exactly k plus 1, what do you know about the black height of its child? Think about it. There are 2 cases, right? Case 1 is that if X is a red node, then the black height of its child would be the same as the black height of itself, right? And the second case is that if X is black, then what's going to happen to the BH of its child? For its child, the BH will be 1 less than the BH of X itself, right? So therefore we have 2 possible answers. The BH of its child is either the same as the BH of X or it's BH of X minus 1. Why do we want to know this about this child? Well, say if the height of X, mean the height of the subtree with X being the root is k plus 1, then what is the height of its children? It will be at most k, right? So for its child, the h of its child would be at most k. And therefore we have assumed that this inequality is true for all its children. So here we go. Since the height of its child is at most k, and therefore this inequality is true for its child, meaning that the size of child is bounded below by 2 times the black height of its child minus 1. And since we know that this one is either this or this, so this one is at least 2 to the power of bh of x minus 1. We take the smaller one because we're talking about at least. Okay, this one minus 1. So we have this inequality. Then what is the relationship between the size of x and the size of its children? Well, obviously we have that the size of x is 1, that's the root itself, plus the size of its 2 subtrees, right? So this is 1 plus 2 times size of child, and size of child is bounded below by this one. So we have 2 times this number, we get 2 to the power of bh of x. And then 2 times this one, we get negative 2. 1 minus 2, we get minus 1. So this inequality is also true for h being k plus 1. So that finishes the proof of this part. Okay, if we have this inequality, let's replace x by the root of the tree. What do we get? The size of the root is what? Is the size of the whole tree. That part will be n, right? And the black height of the root is the black height of the tree. So basically we have that n is greater than or equal to 2 to the power of the black height of the tree minus 1. And we can certainly move negative 1 to the left hand side of this inequality, and we get n plus 1 is greater than or equal to 2 to the power of the black height. So that's where we see log of n plus 1. We take log to both sides and get log of n plus 1 is greater than or equal to the black height of the tree. So next to be proved is this. If we can prove that the black height of the tree is greater than or equal to the height of the tree divided by 2, then we can obtain this conclusion. Now here comes your second discussion question. Please finish the proof.